Hi, today I'm going to show you how to solve a matrix proof by induction problem, but the principles of this hold for all proofs by induction, not just for matrix problems. There are 4 steps to a proof by induction. The first is the basis, the second is the assumption, the third is the induction, and the fourth and final one is the conclusion. The basis step usually involves proving the statement for any given number, usually 1, which means you prove the statement at usually n equals 1. But this can be done for any number, and the proof by induction still works. The assumption then says that because you know it's true for at least one value, you assume it holds for all values n equals k. Now, your induction uses this assumption to then prove that the statement holds for n equals k plus 1. And if we know it's true for one value, and we know that it will always be true for k plus 1, given that it's true for n equals k, then that means we can prove that it's true for all n in the set of z plus by mathematical induction. And we just go over what leads us to that proof in our conclusion. So we're going to try a problem now. Let's say I want to prove by induction that for all positive integers n, the matrix 1, minus 1, 0, 2, all to the power of n equals 1, 1 minus 2 to the power of n, 0, and 2 to the n. Well, first we need to have our basis, so we will try and prove this for n equals 1. So if we evaluate the left-hand side at n equals 1, you end up with this matrix to the power of 1, which is just the same as the matrix. So you get 1, minus 1, 0, and 2. Now for the right-hand side, if we want to evaluate it at n equals 1, we end up with 1, 1 minus 2 to the 1, 0, and 2 to the 1. And this is equal to 1, minus 1, 0, and 2. So at n equals 1, comma, LHS equals RHS. So we've proven it for a given number and we've completed our basis. Now we need to make more space. So we know it's true for n equals 1. Now what we're going to do is assume that it holds for n equals k. So we're going to say that 1 minus 1, 0, 2 to the power of k equals 1, 1 minus 2 to the k, 0, and 2 to the k. And we will assume that this is true for all values of k. Now comes on to our induction step, where we try and prove that this statement is true when instead of k we have k plus 1. So what we write is we do the left hand side 1 minus 1, 0, and 2 to the k plus 1. And we want to rewrite this somehow. Well, we know that with powers we can split them up into multiplication. So why don't we try that? If we say that this is simply the product of 1 minus 1, 0, and 2 to the power of k multiplied by all to the power of 1, which is just the matrix itself. Right? But we know from our assumption that this is the same as this, which is equal to this. So we can substitute that in right there. And we end up with 1 minus 1, 0, 2 to the k plus 1 equals Now, once we're at this point, we can just do some matrix multiplication. Now remember, with matrix multiplication, you do this times this, and then times that, and then you do that bottom row times that, and that gives you your 4 elements of your matrix. So, once we do our matrix multiplication, we end up with something that looks like 1 plus 0, 0 plus 0, minus 1 plus 2 minus 2 times 2 to the k, and 0 plus 2 times 2 to the k. And we get that because we have 1 times 1, 1 times 0, and so on and so forth. You get the point, right? But when we simplify this, we find that the matrix results in 1 minus 2 to the k plus 1, 0, and 2 to the k plus 1. Because look, this is 2, this is 2 to the k, this is 2 can be written as 2 to the 1, and when you have 2 to the 1 multiplied by 2 to the k, we add the powers, same over here, so we end up with k plus 1 and k plus 1 over there. And if you look, this is exactly what our initial statement is, but instead of k, we have k plus 1. So now that we've proved it, we need to have our conclusion. So if I rub all of this out, we can come on to our final step where we write, we proved the statement for n equals 1 by assuming the statement held true for n equals k, comma, we proved it for n equals k plus 1, thereby proving the statement by mathematical induction for all n in the set of Z plus. And there you have a proof by induction.